Greetings, Earthlings. Today I want to go over a very interesting question. This is something that I used to be confused about or curious about in school, but I just never got around to it, or I was busy, no one explained it to me. And that question is, where does the 1/3 come from in this volume formula? Now, some of you may have seen this formula. For those that haven't, I think it'll still be interesting. So the volume formulas I'm talking about are the volume of a pyramid, which is 1/3 the area of the base times the height. And similarly for the cone, we have 1/3 the area of the base again, which in this case is pi r squared h. Alright, so today I want to present an intuitive proof. Later on in a few videos we're going to go over a more rigorous proof, but that's not to say that this is a bad proof. I happen to really like this proof. Alright, so let's start with a very special pyramid, which will be a square base. And now moreover, we're going to make the height 1/2 the side length, so it's going to be something like this. Alright, so here's our thing. We need to find where this 1/3 comes from, and we're going to use our hammer. Again, this is the theme we've been talking about in the previous few videos. And what is this hammer? This hammer will be our favorite box technique. So, you may want to pause the video for a few seconds and think about this for yourselves. And the question you want to think about is, what sort of box can we put this in that will pop out that 1/3? We want to find like a nice box where we can fit in a whole number of these pyramids. Alright, so maybe pause that if you're back with us. Your first idea might be, well, let's just make this the top of the box. So this will be the top, so that points right on the top. And this is just a bad diagram, but basically a box like that. It's not too bad, but it's a little hard to visualize. So actually we want to make a larger box. So we're going to draw a huge cube here. Oop. Falling. So let's say we have this cube. Now, our pyramid, you'll see why we chose the height to be a certain size. Imagine this is the very center of the cube. Right? So, hopefully you can visualize that we could take this pyramid and then we could also invert it or flip it upside down and stack it like this inside of the cube. So now we have two of them, one with the face on the bottom and one with the face on the top. Now if you stare at this for a little bit, you should convince yourselves that there's another few pyramids we can fit in here, and that'll be the 4 on the side. So it'll be this one, this one, and that one. So for example, all going to that center point. So let's say this is your base, going to that point, that's a pyramid. If this is your base, and so forth. So that's 2 on the top and bottom and 4 on the sides, for a grand total of 6 pyramids. But remember, we chose the height to be half the height of the cube, so we don't want to actually know how many pyramids can fit in the entire cube, because our true height is only half of it. So since we can fit 6 in the whole cube, that means we can fit only 3 in the rectangular solid up to here, if we slice it right over here. So, since we can fit 3 into that nice box, we don't want 3 of them, we only want 1 of them, so that's where the 1/3 comes from. So there's our 1/3, which I found to be awesome. Alright, so that's our basic setup. Now you might wonder, well, that's a very special case, right? We have a square base and the height is exactly half of the side length. So what about all these questions? What if the height is not 1/2 the side length? Maybe we have a box that will be like this big, so we'll still do the same idea of putting it there, and you'll see that the top and bottom pyramids will be the same, they'll be identical, but the ones on the 4 sides will look a little different from the top and bottom ones. But that's okay, because let's just for a second focus on the bottom pyramid and the one that's going this way. So they share this side, right? So this pyramid has this side, and this pyramid also has this side. What's different about them is that the height of this pyramid is going to be half of this side length, whereas the height of that pyramid will be half of this side length. So, in other words, if let's say we focus on this pyramid, although this side appears to be double, its height going into the center is only half of that side length. So that doubling and the halving, the 2 times 1/2, means they're going to have the same volume because the 2 and the half cancel out. So although they may look different, all these will still have the same shape. So what we've just convinced ourselves is that this is not a problem. This will work the same way and give us that 1/3. So now you might think, okay, that's nice and well, but what if we don't have a square base? So let's say it's still rectangular, but maybe it's like this or something. So if it's like this, we're going to use our friend, the Cavalieri Principle. Now, I'm not a fan of huge names. To me, this is just common sense. But what is the Cavalieri Principle? It says that if things are equal in terms of, let's say, the area slice by slice, then if we sum all those up, the volumes are equal. So for example, instead of picking a rectangle like this, maybe we take a nice size square, and these have the same areas, and provided they are equally tall, slice by slice, because they're both moving linearly to this point. This is a little bit hand wavy, but hopefully this just jives with your intuition. If we said the bases are the same area, they are going to both linearly decrease up to that point. So basically slice by slice, if we take, let's say, this slice and compare it to that slice, they're always the same area. So if we sum a lot of the same stuff, we get the same volumes. So we can take this pyramid, convert it to this pyramid, and run our same proof just as we did. So that shows us that non-square bases are fine. Now what if it's skewed or tilted? So there's a shape called the parallelepiped or piped, depending on your language. So think of a normal rectangular solid. Now what if we take this and we tilt it so it's like this now? Oops, messed up the connections here, but I think you guys got the idea. Alright, so think of this like maybe like a tower of Jello or something. Slice by slice, they always have the same area. So like this is the same as that slice. So if we sum all of them up, we'll still get the same volume. So in the same way, if we have a skewed pyramid, so that would look something, let's say, like this. We slice by slice, it's no different than if it's symmetric and going up like this, because at each slice, it would be the same. So that takes care of this case. So the skewed thing doesn't matter. We can just think of it like Jello and make it nice, upright, and symmetric. All right, finally, you might say, okay, that's for rectangular shapes for the base. What if the base is not even rectangular? What if it's like a polygon? What if it's like that? Or worse yet, what if it's some sort of squiggly boop? Or if it's a circle or something? As long as it goes up to a point, so this would be a cone, right? And this is just any shape basically. No matter what the size of it, no matter what the shape of your base, we're going to use the same logic and just create a square or a rectangle that's going to have the same area as our base. So let's say we have a circle, we construct a square at the same area as the circle and make this the same height as that, and using the Cavalieri Principle and the fact that things are decreasing at the same speed for both of them and linearly, because these are lines going up, these are going to have the same volumes. That's a little bit hand wavy. We're going to see a more rigorous or technical proof in a few videos, but I actually really like this. So here's the powerful idea. No matter what your base is, whether it's a square or a triangle, it could be a tetrahedron, doesn't matter. That's a tetrahedron. You just take the area of your base multiplied by the height and by 1/3. And that's it. That's always going to be your volume. Cool. So hopefully you enjoyed that. I will see you guys in the next few videos.